This research paper presents a novel approximation method for solving stochastic differential equations, SDEs, which are essential in modeling real-world phenomena that involve random noisy perturbations. The proposed method utilizes quadratic polynomials to approximate the solution between two successive intervals, demonstrating promising results in solving SDE problems. The paper begins by discussing the limitations of ordinary differential equations, ODEs, and highlights the importance of SDEs in various fields such as theoretical physics, molecular biology, population dynamics, and mathematical finance. It also reviews existing stochastic schemes like the Euler-Maruyama, M, and Milstein methods, which are commonly used to simulate sample paths of SDEs numerically. The methodology section explains how to use quadratic approximating functions to develop the algorithm. It focuses on the equation for geometric Brownian motion, a basic model in financial mathematics that describes the time evolution of financial variables. The analysis of stability, consistency, and convergence of the proposed method is presented in detail, demonstrating its efficiency and accuracy compared to traditional methods. Numerical experiments are conducted to compare the performance of the new method with existing ones, showing that the quadratic polynomial approximation method outperforms other schemes in terms of computational cost and accuracy. This makes it a promising tool for solving SDEs. The paper concludes with a discussion about the obtained results and suggests potential future work directions. It emphasizes the need for further research on improving the proposed method and its applications in different domains. The overall summary highlights the significance of this novel approach in advancing the field of stochastic differential equations and its potential impact on various disciplines. The proposed method for integrating the system involves subdividing the interval 0, t, into subintervals obtained from a regular partition, where n is an even number. The goal is to obtain the values of the function x, t, at the next two time steps t2n plus 1 and t2n plus 2. Given the approximate numerical values of x, t, at the grid points t, I equals 0, 1, 2n. The method involves integrating equation 7 on t2n, t2n plus 2, and t2n, t2n plus 1, respectively, and approximating x, t, in these intervals using quadratic interpolation functions. The interpolation functions psi(n), j, t, and psi(n), j, t, are defined by equations 10 and 15, respectively. Substituting the interpolation functions into the integrated equations yields equations 12 and 16, which require the values of x, t, at t2n plus 1 and t2n plus 2. By solving these equations, we can obtain the unknowns x2n plus 1 and x2n plus 2 in terms of x2n. The values of x, t, at t2n plus 1 and t2n plus 2 are calculated using equations 19a and 19b, where alpha n and beta n are defined by equations 20. These coefficients are functions of the model parameters, the time step increment t, and the Wiener process w2n. The process is continued until the final time t is reached. The key idea is to use quadratic interpolation to approximate x, t, in each subinterval, and then use the resulting equations to progress the integration. The proposed method provides a way to integrate the system numerically, using a combination of interpolation and numerical integration. The accuracy of the method depends on the choice of the interpolation functions and the time step increment t. The authors present a comprehensive analysis of their proposed method for approximating the solution of stochastic diffusion equations, focusing on stability, consistency, and convergence. They define mean square stability, requiring the sequence of approximations to converge to zero in the mean square sense, and prove Theorem 1, which states that the proposed method is stable in mean square under certain conditions on the parameters. The authors derive an inequality, 23, that must be satisfied for stability to hold and obtain a general condition for mean square stability, 25. The authors also define local error and mean square consistency, proving Theorem 2, which states that the proposed method is consistent in mean square for approximating the solution of stochastic diffusion equations. The proof involves expanding the exact solution using the Ito formula and comparing it with the locally approximate value obtained from the method. Furthermore, the authors establish the consistency of their proposed scheme for solving stochastic differential equations, SDEs, in mean square, deriving upper bounds for the expected values of the squared errors. They prove that the proposed scheme is consistent in mean square, with errors decreasing consistently under mesh refinement. Numerical results demonstrate the performance of their scheme for solving SDEs, with the authors examining the stability region of their method and comparing it to the implicit M and Milstein methods. The results show that the proposed scheme has a superior performance, with the error decreasing consistently under mesh refinement. Plots of the stability region, stochastic solutions, and error tables illustrate the successful behavior of their approach, justifying the theory of the stability conditions. The author's analysis provides a rigorous examination of the method's performance and convergence properties, establishing the stability and consistency of their proposed method for approximating stochastic diffusion equations. The numerical results validate the theoretical findings, showcasing the method's superior performance and stability properties. The authors present a novel numerical method for solving stochastic differential equations, SDEs, demonstrating its improved stability and accuracy compared to existing methods such as implicit Euler-Maruyama and Milstein. The proposed method subdivides the time interval into subintervals and approximates the drift term using quadratic polynomials. Figure 2 illustrates the stability region for the proposed method in Milstein, showcasing the improved stability of the proposed method for sigma equals 0.5. Tables 13 compare the performance of the proposed method, implicit M, and Milstein in terms of L1, L2, and L infinity errors for equation 35, with the proposed method consistently outperforming the other two methods. The authors also investigate the robustness of the proposed method by simulating 10 trajectories for micro equals 1, demonstrating its ability to accurately capture the behavior of the underlying SDE. The mathematical formulation underlying the proposed method is based on a combination of numerical analysis and stochastic calculus techniques. The comparison to existing methods provides a baseline for evaluating the performance of the proposed method. The paper analyzes the stability, consistency, and convergence properties of the proposed method, demonstrating its superior performance through numerical examples. The authors discuss potential future work, such as extending the method to general forms of SDEs. The paper also provides a comprehensive review of existing numerical methods and their limitations, highlighting the importance of solving SDEs in various fields. The results show that the proposed method provides more accurate solutions and is computationally efficient, paving the way for further research in this area. The linear Steklov method is explored for solving stochastic differential equations, SDEs, with non-globally Lipschitz coefficients, a variation of the classical Steklov method. This approach provides strong convergence and simulation capabilities, making it particularly useful in the context of SDEs. The authors draw upon seminal works by Gard, Mao, and Maruyama, which establish the mathematical framework and applications of SDEs. They also reference Kumar and Agarwal's approximate method for numerical solution of fractional differential equations, noting similarities with their approach. The authors discuss practical implementation aspects of the linear Steklov method, citing Roth's report on approximations of solutions to a first-order stochastic partial differential equation. They highlight the importance of considering coefficient properties involved in the SDEs. The paper's main contribution lies in extending the linear Steklov method to handle SDEs with non-globally Lipschitz coefficients through mathematical transformations and approximations. This results in a discrete time approximation scheme, which is shown to be convergent under certain conditions. The proposed method offers a viable alternative to existing numerical methods for solving SDEs. Building upon established mathematical foundations, the authors have developed a new tool for researchers in this field. Future directions include further analysis of the proposed method's convergence properties and its application to more complex stochastic systems. The linear Steklov method's extension to non-globally Lipschitz coefficients is a significant contribution, providing a novel approach to solving SDEs. This work has the potential to advance research in stochastic systems and numerical methods.